that going? Okay. So last class we started fractions and rational expressions, and what we did was we were looking at simplifying and multiplying and dividing fractions. So that's what we looked at. I gave you homework to do, and a few people emailed me and asked about the homework. So the homework, when you go into the textbook, it says Chapter 1, Section 1 is numbers, and then the next heading in that table of contents says practice questions. That's the homework. So if you push that, it'll take you down, and there's questions, and you need to hand in all of those. So I gave you practice questions. That's what they're called in the book. Practice questions 1.1, so numbers, and 1.2, fractions and rational expressions. So those are the two that you need to hand in next Wednesday. They have to be handed in class. If they're not handed in class, I don't accept them. I have it set so that the solutions pop up at 12:20 right online, and if the solutions are available, you're no longer allowed to give it to me. Okay, so that has to be done in class, and remember, stapled or I don't accept it, so you won't have time to go find a stapler. You have to give it to me in class. Okay, I give them to the marker right after class, and I'm not taking late ones and getting them to mark. There's already going to be 120 to mark. That's a lot. Okay, so in the textbook, they're practice questions. If for some reason you don't have the textbook yet, for this assignment only, I'll email you the practice questions, but you need to email me to get those. Okay, and I'll send you back a file with the questions in it. Okay, so what we're going to do today, is there any questions before I start? We're going to look at common denominators, so adding, subtracting fractions. So just to start with numbers, and we're going to add letters in right away. Okay, so hopefully you know how to do this. So when we want to add two fractions or subtract two fractions, they need to have the same denominator or the same bottom. And that is so that we can compare them. So to do that, we need factors. You need to multiply each fraction by something so that the bottom's the same. So a lot of times it will be like this. We have a 3 and we have a 4. So what would be the common denominator? 3 times 4 is 12. So those are called factors. And both 3 goes into 12 and 4 goes into 12. So that will work for both fractions. So you would take the first fraction and you multiply both the top and the bottom by 4. Why can we do that? Going back to last class, 4 over 4, it cancels. So this new fraction, which would be 4 over 12, is the same fraction as 1/3. They're the same thing because you could factor it, cancel the 4. Same thing here. So 1/4, we want a 12 on the bottom, so you have to multiply that by 3. Whatever you do to the top, you do to the bottom, you do to the top. So 3 over 12. So altogether, we have 4/12 and 3/12, which is 7/12. Now, does that simplify? No. Why not? The factors of the top, what multiplies to get what two numbers can you multiply to give 7? 1 and 7, that's it. Does a 7 go into this? No. So that would be the answer. Now the next type is this. So what's the common denominator for this one? Most people will know that it's 6. Could it be 18? Yeah. So what we did here with 3 and 4, you multiply them together and you get a common denominator of 12. You can always do that. You can always just multiply them together. So 18 is 3 times 6 is 18. You can do that. Without a calculator, it's not always your best bet, because then you're ending up with bigger numbers rather than smaller numbers. So you can do that. I'm not going to do it because it's not the best answer, but it is an answer. Okay, so you can put them both over 18, multiplying the first one by 6 over 6 and the second one by 3 over 3. That's possible. But we can make it easier. 6 is equal to 3 times 2. So the first one already has a 3, so if we multiply the first one by just 2, then the bottom will be 6, and this one already has the bottom 6, so we don't need to change it. Let's put an equal sign here. So this will be 4 over 6 plus 5 over 6, which is 9. Actually, I'll do one more step. Now, does that one simplify? It does. What number goes both into 9 and 6? 3, right? This is 3 times 3, and this is 3 times 2. So 3 over 2 is your answer. You could write 1.5 if you wanted to, or you can leave it like this. But what do we not want to do? Mixed fraction. We don't want to put 1.5, because in calculus that will make everything very confusing. Okay, if you start putting mixed numbers. You can put them for your own use, but as soon as you add letters in, you don't want to be having some letters and some mixed numbers. Okay, now what about if we have something like this? It's right, it's like having a 2 over 1, so we do the same thing. We're going to take this first fraction, and we want the bottom to be 3, so we can multiply this by 3. We'll leave the second one alone. So 6 over 3 plus 4 over 3, just 10 over 3. And that doesn't simplify. So hopefully for a lot of you, I mean, this is review. We talked about when you did fractions, right? But we want to talk about these, and then I'm going to put letters in, and we're going to talk about these. And this is fractions and rational expressions part 1. Later in the course, we do the same rules. I'll go back and say, remember when we had a case that was just one single number with no bottom plus a fraction, and now we've got letters in it, so what do we do? So we're going to go back to these. So I want to always show you what it is you already know, and then we're going to add on to it. Okay, so bear with me if you say, oh, this is so easy, okay, because we're going to make it harder. But we want to remind you of what you already know. So you do already know something. Okay, I'm going to make this a bit harder now. So we could just multiply 8 times 6, which is 48, and say that's the common denominator. But is there a better one? And when we get letters in there, you don't want to ever just multiply the two numbers, even though it would work, because what you end up having is some weird factoring that you'll need to do later, and you'll actually end up with the wrong answer half the time. So we want to use this technique, which is, look at the factors of 8. I'm just going to write them out. This is 4 times 2. Does that break down further? 2, 2, 2, yeah. So that would be as far as I could go. Do you agree? That's okay? This one. 3 times 2. I'll just write it down here so they're on the same level. Okay. So what do they both have in common already? Let's circle it. Anything else? No. So they both have 1, 2. Now we want them to be the same, but they all both already have 1, 2. So that one's okay. So kind of ignore that one for now. If we want them to be the same, one of these 2's we're ignoring. What do we need to add in so that they have the same thing? So what you need to say to yourself is, so this first fraction has 3 2's. What does this one have that the first doesn't? A 3. So we're going to add a 3 in. Okay? So now this first one has a 3 and a 2, which the second one has. Now what's missing from the second one that's in the first one? 2 more 2's, or a 4 if you want, but 2 more 2's. Whatever you add into one of these, you have to do it both to the top and bottom. So now do the bottoms, the denominators, have the same 4 numbers? Yeah. So what is that number? 2 times 2 times 2, 8 times 3, 24. So we've got 21 over 24. And 5 times 2, 10 times 2, 20 over 24. And we would leave it like that. So tell me the steps that I did here, because even though you don't quite do this when you're just doing numbers, when we do it with variables, we have to do these steps. So what was this first step? What do you call it? Factoring. So I factored the number on the bottom and factored it again until it was in its smallest factors. So this I factored the denominator. And what could we call this step? What did I do here? Yeah, created a common denominator, looked at them to see which ones was missing, however you want to call that step, okay? So so in your head when you do math, a lot of times people that are not very good in math, they don't have the words to talk to yourself as you work through a problem. So instead what you do is you sort of memorized what a problem looked like, and then you try to recreate that, but you don't actually talk to yourself. In order to do math effectively, you need to have the words to go with it. So say you were English, if you're not English, then make the words up in whatever is your first language. You say, okay, I've got two fractions I need to add together. So first I need to factor the bottom. Next, I need to compare the factors and make sure they both have the same. And if they don't, I need to multiply both the top and bottom by whatever's missing. And then, what do? Add the tops, leave the bottom the same. Right? Whatever your words are for your step, you need to be able to say that over and over again every time you come to a question that's a fraction plus a fraction. And if you don't get the words to go with it, you just look at it and say, oh, I don't remember what to do. Even count the steps. Okay, whenever I do this, there are 4 steps. Right? And that's how you would study. You'd say, here's step 1, step 2, step 3, step 4. Whether it has letters in it or numbers in it, these are the 4 steps I need to do.
Basically with the lowest common multiplier?
Yeah, that's another name for it, yeah. Or multiple. Yeah. Least or lowest, yeah. Okay. So these same techniques work for subtracting. We subtract the tops once the bottoms are the same. So let's go through the steps. The first step is factor the bottom. So this is 3 times 10. Can it factor further?
Yes.
3 times 5 times 2? 9 times 2. Oops. Okay. Now I've added something new into this one. Any ideas what it is? Anyone see anything?
5 and 1 and 3 and the other two. Not, can't easily get a 3 out of the 5.
No.
There's different numbers that you could have put on the bottom, like 6 and 3 instead of 9 and 6.
Yeah, you could do that. That's not what I'm thinking of.
Subtracting.
Subtracting is different, but it's not the same. I'm not going to do the same thing as my next step. There's something. These fractions were not in their lowest to start with. These fractions are not in the simplified form to start with. Well, how do I know that? Especially if you look at this second one, what do you notice? There's 2's that can cross off. Put them in their simplified form before you do it, because then you're just making things bigger. If you keep making them smaller as you can. What about this? Does this one simplify some? It does too, because 8 is 2 times 4, and there is a 2 on the bottom. So let's do that. Let's simplify this. This is 4 times 2, and the 2's will cancel. So I have 4 over 3 times 5. Here, these 2's cancel, so I'll have 1 over 3 times 3. All right. Do you agree with that? All right. Now, what do they both have in common? 3. So we're going to sort of forget about that. What's missing over here? Another 3. So we circled the 3 because they already had the 3. So we need another 3 to have the 2 3s. The second one had 2 3s. One of them was already in common. What else is missing from over here? A 5. So now the bottom, or the denominator, has 2 3s and a 5. And remember, in multiplying, it doesn't matter the order, because 3 times 5 is 15. 15 times 3, 45. 9 times 5 is also 45, right? As long as you have the same factors, it works out to the same number. So what do we have here? 12 over 45 minus 5 over 45. Now, don't simplify these. You want to keep them the common denominator. They're not simplest, but once you put them together, then you can simplify. So we can simplify individually before we start, if they weren't in the lowest form. But once you put that common denominator in, don't accidentally simplify it, because then you're going back to where you started. Do you see what I'm saying? Don't say, oh, 5 and 5, that's 1 over 9. Well, you're going back to 1 over 9 right here. We were making the 45 the same. Once the bottom's the same, just subtract or add the top. So 12 minus 5. Does 7 go into 45? No, so that would be the end. Okay, so I added a new little thing in here. It's that at the beginning, you could always say to yourself, do these simplify before I start. And now, once they're the smallest, then I start. Okay, so that was what the difference was here. So the question I just said, before you start, say, do these simplify before I start? The first one does. What number goes into both 55 and 88? 11. So we have 5 over 8 minus 1 over 8, and we don't need to do a common denominator. If we hadn't simplified before we started, what would we have done? Right, we would have multiplied this second one by 11 and 11 to have 88 as your common denominator, and then we would have done 55 minus 11, and then we would have had to simplify. You'd have bigger numbers. It would be easier to simplify first and then not have to do a common denominator. This is 4 over 8, which is what? 1/2. Now these same thing work if you have more than or more than 2 fractions. So you need the common denominator for all 3. This is 2 times 4. And the other 2 don't factor. All right. So what do we need? What are the numbers that are on the bottom here? We've got a 2 in some of them. We've got a 3, and we've got a 4. Those are the 3 numbers that we see across. A 2, but there's only one 2, so a 2, a 4, and a 3. So what would I need to make a 2, a 4, and a 3 on this first one? A 2 and a 4. So do it to the top and bottom. So what we had here was a 2 over 3. The second one, we just need a 3. And the third one has a 2 already, so we need a 3 and a 4. And then just look, okay, we've got all three of the same factors on the bottom, so we can multiply these out and get three numbers. 2 times 2 times 4, 16. And on the bottom, we've got 24, 9, 12. And remember, once you have a common denominator, don't simplify them by accident. Say, oh, I can cancel that out. People do that all the time. And then you get all confused. What did I do that for? So what we now have is 16 minus 9 plus 12 over 24. Now, when we're adding and subtracting numbers, say at a list of numbers to add and subtract, do you have to do them in order from left to right?
Yes.
No. What I just did to do this in my head to get 19 was this. I did minus 9 plus 12 is 3, and then I just added 3 to 16. Yep.
When you pulled 2 and 3 and the 4 out, on the first line there,
Yeah.
how come it was in the 2 times 2 times 2 times 4?
Oh, well, this does have a 2 and a 2. Let me just, this is 2, 2, and 2. Okay. So, you want them all to have the same thing, right? These two already have 1, 2. So this also needs 1, 2. Okay?
So you just take the other 2.
Well, the other twos, there's nothing else with 2 2s, so we need those 2 2s to be both here and here, which I just called it a 4. I could have called it 2 2s. So I added that 2 2s here and here because this one already had them, but these two didn't. I should have broke that down and said, okay, we need 3 2s on the bottom of each. Yeah. This one already has 1, so we need 2 more. But I had just called it a 4. So, yeah. So, here I should have said 2, a 3, and 2 more 2s. This is what we need on the bottom of each. Okay. So this example it's maybe not as obvious what the factors are, but what factors go into both of these that we know of? Maybe 15 or 5. 5 for sure, right? Because they both end with either a 0 or 5. So 30 is 5 times 6. Can that break down further? Yeah. Now 105, so I showed you how to do this. Actually, I think we might have used this number before. So if you know that 5 goes into it, how do we know 5 goes into it? Because it ends with 5. 5 goes into 10 how many times? Twice. And 5 goes into 5 once, so that would be 21. 2 and 1. 21 does break down further. 3 and 7. Okay. So looking at the 2, what numbers do we need on the bottom? We need a 5, a 3, and a 2. That's the first one. And a 5, we already have it. A 3, we already have it. And a 7, we don't have that yet. You need all the numbers on the bottom, but only as many times as they appear on each. So we want the 5 and the 3 already in common, so we need to put a 7 on this one and a 2 on that. So those are the 4 numbers that we need. So on the first, we need a 7. And on the second, we need a 2. And what does this work out to be? I don't know. We could work it out. 30 times 7, which is 3 times 7 is 21 with a 0 on the end. Seven minus 8? -1. Be careful of your signs. I know a lot of people get signs wrong. You'll just have to practice. What about dividing by 0? Like, say, 2 divided by 0. No, so we say we can't divide by 0. In calculus, they're going to actually go back and say, well, we can divide by 0, and this is how you figure it out. But for now, remember I told you that another class? I said in math they teach you stuff that, and they say that's not possible, and then later they say, well, actually it is. So 0, right now, we're going to say is undefined. Okay, so there is one on the homework that you end up dividing by 0. Yeah, and the answer is there's no solution or undefined. Yeah. What happens when we take, let's go back to like a pie or a pizza, and we cut that pizza into 2 pieces. There's 2 people in the room. How much do they get? Half. 1 pizza cut into 2 pieces. And you can picture what a half is. Now, 2 more people walk in the room. What do we do? So, do you get more or less pizza, each person? Less. I'm going to make it work nice. So let's say 4 more people walk in the room. What do? All the 4 people that are there have to divide their piece in half. So that's 1/8. How big are your pieces now? Smaller. What if this kept happening? And you weren't greedy and you did keep cutting your piece in half? Let's say there's 100 people in the room. It's still the same pizza. It didn't get bigger. I'm not going to draw 100 pieces. But what happens to each piece? If I do this enough, they'll look small, right? Okay. So let's say like 1/100. How big are those pieces? Very small. In fact, at some point, you're not really going to be able to do it anymore, right? Probably at this point, you may not be able to do it. What's going to end up to the pizza if you keep doing this? Yeah, it's going to be mush, right? Like, it's really not going to be, maybe someone would eat it with a spoon or something, right? But some of us would just say, no thanks, that doesn't look very yummy, right? It's mush. So what about 1/infinity, cutting it into infinite pieces? What do you think? Still 1 pizza, still 1. So 100 pieces might be mush. Infinite is not possible because you just keep cutting and cutting and cutting and cutting. But how big are the pieces? Yeah, they're close to 0, right? Because there'd be no pieces left. They get smaller, 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 and you keep going forever. How big is your piece? Gone. We don't say it's equal to 0, we say it approaches 0. So this little thing means approaches. Does that make sense that it would approach 0? Like the size of it's getting smaller and smaller until it's gone? Right? Infinity is not a number. Infinity is an idea. Because you can never get there. So what's infinity plus 1? What's infinity plus 1? Still infinity. Because you can't get bigger than infinity. Infinity doesn't stop. It's an idea of the biggest number, but you can't ever get there. 2 times infinity? What about infinity minus 10,000? Still infinity. Infinity minus a million is still infinity. You can't, the only way to not be infinity anymore, what could we subtract? Infinity. But that's not equal to 0. Only sometimes. How confusing is that? Not necessarily, it might be equal to 0, might not be. There's actually techniques that you'll learn in calculus to figure that out. So what we call, say, 0 divided by 0, infinity divided by infinity, infinity minus infinity, 0 to the 0 power, infinity to the 0 power. What else? What other combination? Infinity to the infinity? Actually, that is equal to infinity. What else? 0 to the infinity? These are all what we call indeterminate forms.
What's the difference between that and undefined?
So indeterminate form means there is an answer, but we're not sure what it is until we do something else. So it's indeterminate. We can't determine it by just looking at it. We need to know what context it's in, where it comes from, and then there's a way to figure it out. Because, say infinity minus infinity, for example. So I say infinity is an idea. It's just like the biggest number. So it might be bigger if you're both counting to infinity and you're way out there. So one of you might be quicker and be ahead of the other. So maybe you're both at infinity, but one of you is bigger than infinity than the other infinity. It's weird, I know, to think of. So if this is bigger, then that might actually not be equal to 0, because one person may be further out than the other. So it could be not infinite, not 0. It could actually be a number. So that all being said, right now in this class, when we see these things, we just say undefined or no answer or whatever you want to put. Does not exist, whatever. Later on in calculus, they're going to show you that these things all do exist and they have an answer. I put these ones in here. What do we know about a power of 0 usually? No? Yeah. So if we had like 2 to the 0, that's equal to 1. Now that's a thing we often say, just memorize that, right? When we get to the exponent section, I'll show you why it's equal to 1, and then hopefully you'll just know that. Okay. Let's add variables into our fractions. And what did I say fractions with variables are called? Rational expressions. Okay. So rational expressions are fractions with variables. So we'll start easy. We've got an x on the top here. We do the same thing. We want to find a common denominator. So 4 times 3, or 2, 2, and 3. So the first one we're going to multiply by 3. And the second one we'll multiply by 4. So what's x times 3? 3x. And it's fine to say x times 3 is x dot 3, but you don't usually say x3. That looks weird. All right, I think you all know that. So 3x over 12 plus 8 over 12. They have the same bottom, so we just add the tops. And you can't add them, so you just leave it, because we don't know what x is, so we don't have an answer. So that's it. That's the answer. Yep.
9, if the 8 looks like a 9, can't you simplify it all together?
Yeah, and we'll see that soon. Yeah. So. Okay, the next one. 2x over 3 minus x over 9. What's the common denominator? 9. So we multiply the first one by 3. The other one we don't need to multiply because it's already a 9. So what do we have on top of this first one? Yeah, 2 times x times 3. Remember, that's 2 times x. That 2 is not attached to the x. So that is same as 2 times 3 times x, which is 6x. So 6x minus 1x over 9 is 5x. So where the first one, it was just an 8 without an x, we couldn't add it. And the second one had both of them an x, so 6x's minus 1x is 5x's. Actually, let's go to the next page. Yep.
Before, you said the x isn't attached to the number,
Right.
so why would you say
Oh, okay. So you're saying like x minus x is 0 or something? Okay. Let's try this, okay? So if we're factoring, I don't know if you remember factoring. So if we had like 2x cubed minus 3x, they both have an x in them, okay? So we can take an x out of each. We sort of did this with numbers the first day. So if we take 1x out of here, what do we have left? We have a 2 left and an x squared. Do you agree with that? And if we take the x out of here, what do we have? 3. Okay. Now you say, what on earth does that have to do with my question? I want you to go up here and do the same thing. So if we were to take an x out, because they both have an x, what do we have left? So if we take this x out, we have a 6 left here, minus, if you take everything out, what do we have? 1, because this is like x times 1. So now what we have left is x times 6 minus 1 is 5, which is 5x. I don't know. Is that... So I apologize. And you can question me anything. I just don't know if I can always answer a good way that will help, because sometimes it's really hard to... I'm sure you've experienced that before. If there's like a professor that knows stuff and they can't sort of get down to what you're actually asking, so just question me. I'll try. Okay? That's one way to explain it. I think the normal way they explain it way back when you first start algebra is like if this was 6 apples minus 1 apples, you would have 5 apples. But the problem I have with that is that that's where I think you got this idea that the 6 is attached to the x. when it's 6 times x, like it's 6 times 1 apple, which is 6 apples. I don't know. And I find that people want to keep that 6 on the x, and they don't think of it as anything else. So I think factoring might help.
It's not really a question, it's just to go with your explanation. You would do 6 times x first, and so you would have 6 x's all together. If you wrote them.
Yeah, and you wouldn't, and that's the problem, because you actually wouldn't have x times x times x times x.
That's where the complication.
Absolutely, because it's not 6 x's, and that's why I don't like that 6 apple thing, right? Because you're picturing 6 apples in your head, so you're picturing 6 x's. But how do we actually write 6 x's? X to the power 6, not 6 times x. So that's where I think it goes wrong with people, right? And that's why I don't like if you had 6 apples and you take away 1, that does make sense, but it's not that you would write out 6 x's in a row. This is a 6 and an x as separate things multiplied. So I think the fact.
No, because it'd be different if it was like 6x squared, you couldn't subtract from the x, because
Yeah.
an x and an x do 1 power each.
Yeah, and that's not 2 apples minus 1 apple. Yeah. So it's hard to do it that way. All right. And sometimes in math, when we get confused, we're thinking too hard. And then you get all confused, right? You're thinking it's more complicated than it is. What's the common denominator here? 6. So here I've got 2 terms on top of each fraction. Okay, so this, when I multiply this first one by 2, I'm not just multiplying the 1 by 2, I'm not just multiplying the 5 by 2, I have to multiply the whole top by 2. Because it's factors. So we had one thing on top, which was 5x plus x, that was one thing, and we're going to multiply it by 2, so that it's still the same fraction. Over here, we're going to multiply it by 3. There was already a 2, and we're going to multiply by 3 on top and bottom. But again, it's the 2x and the 1 that we're multiplying by 3. So to do that, you actually have to multiply that into both pieces, which we call expanding. So here we've got 5x times 2 is 10x, plus 1 times 2 is 2. And here we have 6x plus 3. 2 times 3 is 6, and 1 times 3 is 3 over 6. Now there's a further complication in here. We're subtracting. What are we subtracting? What do you think of this?
Just group your like terms together so that it looks easier. Because then you know that you have to subtract just the x's and then just the whole number together.
Yeah, this is wrong. This would get marked wrong. What's wrong with it? Right, I need to subtract this whole fraction, which is the whole top. All of these pieces of pizza have to be subtracted, not just the 6x part, the whole thing. So this would be more correct, because that minus sign has to apply to both of these. So this would be 10x plus 2 minus 6x minus 3. We have to subtract both. And then you collect like terms, right. So this is 10x minus 6x. We can subtract those two. And a plus 2 minus 3. So I just rearrange them. So 10x minus 6x is 4x. And 2 minus 3 is minus 1. And that would be your answer. Okay, so there's a couple things in here that you have to look at. Common denominator 6, fine. But you have to multiply the whole top by whatever it is you're multiplying in the whole top. So that would involve expanding. But if there's a minus sign, that also has to apply to everything after the minus sign. Just on top. Because whenever you do any fraction, you're only adding or subtracting the top. You're making the bottom the same pieces, so they're comparable. And then you either add or subtract the top. Okay, So next class, we're going to continue with rational functions, but we're going to put the x's on the bottom, which adds another layer, okay? So stay. If you're not registered in my class and you want to be registered in this class, stay and I'll get your name so I can put you in the course.